So I have started the recording. Yes, yes, I have started the recording. Okay, there are only two people, Patlika and Shivam. So welcome you guys. Today is our fourth live lecture, and I will be solving few questions of assignment 2, 3 this year and previous year also. So are you guys able to see my screen? Yes, Patlika is able to see. Okay, my and my screen is moving or not, are you able to see? Okay, I hope everything is fine. So okay, so try to solve this question. I hope it is visible to you. Yes, so the question is given that in a molecule the radiative transition is much faster than the vibrational relaxation. In this case the stroke shift would be. Have you read the question? Yes, tell me what is the, have you understood what, which answer is correct? Yes, so answer would be D. Much lower comparable to a molecule for which the radiative transition is slower than the vibrational relaxation. So the question, so look at this image. The first one here, it says that here the radiative transition is faster. So this is the stroke shift here. Okay, and in this case the radiative transition is so fast that it doesn't have much time to relax, so the stroke shift is less. So this is the condition given in the question. that the radiative transition is much faster. So which means the stroke shift will be less or lower comparable to this. So yes, you are correct. Okay, moving on to the next question. For an accurate measurement of the emission spectrum, one need to correct intensity profile obtained on a detector. This is because of the absorption of the light by the sample, non-ideal behavior of the monochromator and detector, non-ideal behavior of excitation light source. The conversion of the light to electric signal by the detector is quite low. Oh, screen not moving. Now, now try to solve. So out of these, like what are the possibility? This can also be possible. This is also possible. Not ideal behavior of excitation light source. That is also like one of the factor which creates problem or which deviates the true spectrum measured by the fluorometer. So out of these, how do you like which first tell me which one is correct? Yes, B and C both are actually correct, but here it is written that non-ideal behavior of monochromator. So for an accurate measurement of the emission spectrum, one need to correct the intensity profile obtained on the detector. This is because of the B and C both should be the answer. I don't. Okay, again it is. So according to me, these two should be correct. B and C. That is why in the emission spectrum we used to S1C by R1, because this is for sample. This one is for reference. This is your correction file. So I so reference means we have to normalize what the observed signal because of the fluctuation in the light intensity or the excitation source. So that is why this should be uh, this should be normalized. The um, I mean the obtained signal should be normalized. So that is why I think B and C both should be the answer. And monochromator and detector, uh, they are they are not ideal. What do you mean by ideal? That ideal means at all the wavelengths. Let's say their efficiency should be like this at all the wavelength. It's but in actual, like in the real world, nothing is perfect. So the detectors like this behaves like this. So at this wavelength the efficiency is low, at this wavelength efficiency is high, at this wavelength efficiency is less. So which means it will give you the wrong spectrum. So that is why we have to correct it, and because of this correction file comes. And also similarly for the monochromator, so not all the wavelength efficiency lambda, it ideally should be like this, which means what does it do? It basically disperse, it actually basically disperse the light, but the efficiency of dispersing the light is not that high, is not constant. So it also, let's say it is behaving like this. So that is why we have to correct our emission profile, or this emission spectrum. So this is the correction file, and this is the signal we have observed in the detector of the sample. So in the emission spectrum we have two detectors. I hope you have seen the lectures. Okay. Okay, nobody else had joined. Yes, okay. Okay, moving on to the next question. The question is, for statements regarding fluorescence lifetime are given below. For for four statement regarding fluorescence lifetime are given below. The correct statement is, the fluorescence lifetime varies with the excitation light intensity. Fluorescence lifetime does not depend on the concentration of the sample. Fluorescence lifetime is inversely proportional to fluorescence quantum yield. Quantum yield. I think this is the formula. So are these correct or not? I think they are correct, right? Yes. So quantum yield should be directly proportional to tau, because this is tau. Yes. So this statement is wrong. Fluorescence lifetime varies with the excitation light intensity. So actually it does not depend on the excitation light intensity. Lifetime means, let's say this is your ground state, this is your first excited state. So from here to here you have excited. Now it will radiate from here to here. So lifetime is how much time the fluorophore or the molecule is spent at S1 state. That is the lifetime. So it doesn't depend on the excitation light or anything intensity. So this is also wrong. What about the second one? B, fluorescent lifetime does not depend on the concentration of the sample. Oh, concentration. This you need to explain it to me. Does it really depend? Let's say I am taking concentrated sample. What? What true? It doesn't depend on concentration. Yes. So fluorescence lifetime does not depend on the concentration of the sample. Yeah, this is the inherent property of the molecule, the lifetime, that how much time it will spend on the excited state. So, which means, yeah, option B is correct, right? And what about the option D? Average fluorescence lifetime is time when 63% of the excited state population comes back to ground state. Yes, that statement is also true, because this is the intensity at time t. Let's say it is if average lifetime has 60% population come back to, so basically this I by I0 is equal to E minus T by tau, and this time T time will become tau when, let's say at condition, at any condition, it becomes T equal to tau. So you can, by back calculation you can calculate it. So it will become I by I0 will become e to the power minus 1, which means I by I0 1 by E, and E equal to 2.37, something like this, if I am correct. Let me check it. Yes, it is 2.71, so I was correct. It is 2.71. So if you divide this 1 divided by, I think you will get 0.37. 1 divided by 2.71. So it is coming 0.37, 369. So it is 37. So now you can figure it out. It is I by I0 equal to 0.37. The ratio of intensity at time t, where the t becomes your lifetime, I equal to I0, which means that the intensity of your excited state population now is only 37% left, which means 63% is decayed. So that is your called lifetime. So that statement is also true. So I think maybe they have given this MSQ type question, multiple select question, because in this question also two options were correct, and here also two options are correct, B and D. B and D. Okay, moving to the next question. In an absorption spectrophotometer, the detector is kept in the front of the incident light to the sample, but in the fluorimeter, the detector is placed at the right angle of the incident light to the sample. This is because the sample only emits fluorescence at particular direction of the excitation light. At right angle geometry, the polarization is minimum. The scattered light is not desirable in fluorescent measurement. At right angle, the diffraction of the fluorescence through emission monochromator is minimum. This you need to answer. This is simple. Yes. So let's say this is your C. Yes, C is the correct answer. So let's say this is your excitation light and this is your sample. If you kept your detector here, kept your detector here at this position here. So this is the setup for absorption and here detector for emission, because this light will excite your molecule and this molecule will emit, and the emission is directionless. But if you keep your detector here for fluorimeter, it will also detect your excitation light, so it will suppress your signal of emission. So that is why we have to kept it here, because there is no problem, because it is directionless. We can so that is why we are collecting at 90 degree. So option C is correct. I hope it is fine. Okay, so let's move to the next question. With increase in the concentration of the fluorophore, the fluorescence intensity will. You need to answer. Okay, at this condition, is it visible to you, or can I keep it like that? The screen is visible to you? Okay, 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 fine. So what is the answer of this question? C, yes. Because this is your intensity, this is your concentration. So as we increase the concentration, intensity will increase, but up to certain concentration it will increase, then start decreasing and it will come back to zero, because of the inner filter effect. Because as you, let's say this is your cuvette, the sample is dilute, so light will come, it will also, it will reach till here, because here also slits are there. In the fluorimeter we have slits. This is excitation slit, this is emission slit. So only this part is going to the part, this part is going to absorb the molecule, absorb the light. Hence, hence and in another condition, if the concentration of the sample is higher, what will happen? Much higher, let's say much higher, the light will not go, it will not reach at this point here. So it will absorb here only, but slits are here, these slits are here to here is the detector D, here is the detector D. So it will not going to absorb any emitted light after certain concentration. So that is why the intensity will keep on decreasing. So that is because of the inner filter effect and front surface absorption. Fine. Kasa's rule is not valid when a molecule shows fluorescence from higher excited state. A molecule undergo internal conversion to S0 state. A molecule shows fluorescence from lowest vibrational level of S1 state. That is the Kasa's rule. Vibrational relaxation is very fast in the molecule. So what is okay? You are given the answer A, yes. Which is because Kasa's rule says this one, this one, S0, S1, S2. So let's say these are the vibrational states. The vibrational state I am drawing with this color. These are the vibrational state. These are the vibrational state. So Kasa's rule says that molecule here present here will go here at this position, then it will vibrationally relax to its ground vibrational state, of first excited state. Then from here it will come back. So this will give you fluorescence emission. This is Kasa's rule. But there are for few molecules or there are other systems which can also go from this position to here, and they can emit from here only, here also, from here. So this is not following Kasa's rule, not following. So that is why the molecule shows fluorescence from a higher excited state is not valid according to the Kasa's rule. Fine. Okay, moving on to the next question. The excitation spectrum is not same as the absorption spectrum when the system contains a single fluorophore species and no excited state reaction are happening. Undergo radiative transition from lowest excited singlet state. Concentration is very high. So different species stabilizes the excited state differently. Answer is written, no? You have to give the reasoning. Reasoning also written, but I want to know how much you have understood. but light will not pass. It doesn't mean that all the light will stop. Inner filter is like uh, inner filter is like this. No, let's say at this higher concentration, this is also higher concentration intensity. So why? No, we will get the excitation spectra. No, even if the concentration is high. Acha, concentration is very high, so which means that it will not pass the light. That's what you mean. Light does not pass. Inner filter effect will occur. We did not get the true excitation spectrum. Not observe the excitation spectra higher. So if the concentration is high, which means light will not pass. But reasoning is written here something else. At high concentration, apart from the monomer, many other species like dimer, oligomer, or aggregated species may form, and the system becomes heterogeneous. So, different species stabilize the excited state differently, which leads to different excitation spectra as compared to absorption spectrum. I'm also see at the high concentration. I think in the yeah in the excitation spectrum instrument scan excitation wavelength at the fixed emission wavelength. In the excited instrument scan excitation wavelength at the fixed emission wavelength. So The reason that are written not convincing. I don't know. See, I think reason is like, let's say if you are able to absorb the absorption spectrum. At high concentration, so what will happen? Let's say your absorption spectrum, if that is too high, if the NN filter is happening, that which means that you will not also observe the absorption spectrum also. I'm thinking that way. If that filter effect is coming, yes. So if that is the case, then you will not get the signal. I believe so. Because the, and this reasoning is also like kind of convincing, because at the high concentration, this is a chance for forming the monomers, forming the dimer, oligomer, other species also. So if that is the possibility, then the sample become heterogeneous, obviously, which means if you excite the molecule, let's say monomer will excite. So if you the sample is heterogeneous, so if you excite the molecule, which means you are exciting monomer, dimer, oligomer all together. So in the emission, so excitation spectrum, by fixing, you'll get the excitation spectra at at a any particular fixed wavelength. So at that particular fixed wavelength of emission maxima, you are getting that emission from all the species. So I think that is why you will not get the same excitation spectrum, because inner filter effect means the concentration is too high, your intensity is dropping after some point, after some concentration, because light is not reaching at this position. It doesn't. This effect is about the concentration. It does not said about anything that it will change the nature of the spectrum. So let's say system is heterogeneous. And this heterogeneous system you are exciting here. So let's say one monomer is excited, dimer got excited, oligomer got excited, and you are getting the emission from by the average of emission of all these species altogether, the average of these species altogether, and you are fixing, let's say, this wavelength of emission maxima, and try to find this is the lambda, the emission, this is the lambda max of emission. So at this wavelength, let's say you are observing, collecting the excitation spectrum. So this is the collection of all the species. So maybe in the absorption, the your absorption maybe it will look like this, but this is absorption. But in the excitation, you'll get like Most probably, if the difference is high between two peaks, so you will get the separated peaks. Let's say one, two, or three. So you'll determine that one species, second species, third species, three species are there. One, two, and three. If the difference is too high, resolution is like the difference between the two peaks are higher, then you'll get the separate peak. So I hope you are clear. Okay. Okay, moving on to the assignment week. This this is the assignment of uh, week 3. So the first question is, in a fluorometer, MgO is placed at the sample position. Both excitation and emission monochromator are scanned simultaneously. The primary purpose of this experiment is to absolute fluorescence quantum field, lamp spectral profile only, combined wavelength dependent sensitivity of emission monochromator and detector. So MgO, this is the scatterer. So this is using, if we are using this is kind of a scatterer, which means that we are somehow correcting our instrument. In time correlated single photon counting TCSPC instrument, we also use scatterer Ludox, another scatterer also milk. You can also use milk also, but anyway we use in laboratory, we use Ludox. So using the scatterer means these molecules don't have any lifetime, they just scatter the light. So even if you're getting any lifetime in the TCSPC instrument, which means this is the instrument what we call instrument response function, IRF. Because so which means that this is the problem in the instrument, IRF. So that is why when before taking the any lifetime measurement, we first take the this IRF using the scatterer, and then take the lifetime. And when we fit and try to find the component of the lifetime, we always deconvolute this instrument response function, because this is the kind of the um, uh, what you call incorrect measurement in the instrument, or noise. I would not say noise. Anyway, so here Mg also placed at the same position. Both excitation and emission spectrum are scanned simultaneously. The primary reason of this experiment is to determine the combined wavelength dependent sensitivity of monochromator and detector, because I have already discussed in this class and previous class also, this monochromator and detector are not ideal. So we generate first the correction file, because no two monochromator or detector ideal or same in this world. So that is why we have to correct the emission file, or the spectrum, emission spectrum. So that is why we use this scatterer. And what is the, so answer is C. And what is the explanation? MGU scatter all the wavelength equally, therefore any wavelength dependence is detected. Signal arises only from the instrument response. That is what I was telling you. So any detected signal arises from instrument response, monochromator plus detector. This gives the sensitivity function. This, I hope it is clear. Yes, okay. This is first, this is second. Okay. Why is a quantum counter preferred over a normal photodetector for correcting excitation spectrum? A, it response its response is proportional to photon number, not energy. Yes, this is correct. It emits light proportional to wavelength. No. It measures fluorescence lifetime. No. It removes inner filter effect. No. It works on the principle of inner filter effect. So answer should be A. Yes, answer is, explanation is, lamp intensity varies strongly with the wavelength that we have already talked about. A quantum counter convert incident photon into fluorescence with constant quantum yield, because the concentration in this quantum counter is too high. That is why the fluorescence, that is why the quantum yield quantum yield of all the at all the wavelengths are constant, making output directly proportional to number of photons. I hope you are able to see my screen because connection is lost. Hmm. So making output is directly proportional to number of photons, enabling accurate correction. So if you not sure, you can watch the 10th lecture and 11th lecture of basics of fluorescence spectroscopy. Okay, moving on to next question. Next question is, a fluorophore shows strong red shift in emission but negligible shift in absorption with increased solvent polarity. This implies, this is simple, you need to tell me with explanation. Hello, am I audible to you? Yes, you have written something. Excited state is more stabilized in polar solvent compared to ground state. Yes, your explanation is correct. So what happens is that, let's say this is ground excited, ground excited. This is your ground. This is P1. This is P2. Polarity of P2 is higher. So, and also given that mu E is greater than mu Z. Dipole moment of excited state is higher than the ground state. So this will going to, so what will happen if the polarity, if you dissolve a molecule in a higher polar medium, it will stabilize more compared to your ground state. Hence the difference between this, let's say E2 in here, E1, so here the E1 will be higher than E2, hence lambda 2 will be higher than lambda 1, hence this is redshift. This is what given here, redshift. So which means the excited state is significantly more polar than the ground state. Option is B. Is it okay? Okay, you got it. Okay, moving on to the next question. An observed emission intensity at 520 nanometer is this. The instrument sensitivity function at this wavelength is, okay, so sensitivity function depends on the wavelength. So absorbs, this is absorbed and this is true, and this lambda here is 520. What is the true emission? This is they are asking. So sensitivity is 0.6 and absorbed is 22 AU arbitrary unit, and I true, you can calculate it out. I true is equal to 240 divided by 0.6, 400 AU. Answer is D. Is it okay? So you know about this formula, this one. Because the sensitivity true is true means true means the actual, but whatever you are observing, because it should it it definitely will be low uh, than the actual intensity because of the non-ideal behavior of the monochromator detector, or because of the light intensity. So that is why the sensitivity function comes into the picture. We always multiplied by C when we observe the when we observe this S1 C by R1 divided by no, this is the, and this wavelength, and we observe the emission spectrum. Okay. Yes. So this is the sensitivity function comes into this correction file, this here. So I believe so. This is good. Okay, moving on to the next question. Question is, a sample has an absorbance of zero point 0.4 and is dissolved in a solvent with a refractive index of 1.4. A reference compound has an absorbance of 0.5. Quantum yield of this is this 0.55. It dissolved in a solvent with a refractive index of this is 1. Okay, X is sample and S is standard. Okay, 1 point the ratio of the integrated fluorescence intensities. This ratio is given here. It is 0.9. Calculate the quantum yield of the sample. So we need to calculate the quantum yield of the sample. So we know this formula, right? This formula. Just apply this formula, you'll get it. This means of X is equal to quantum yield of this is given 0.55. What is the absorbance of your standard? It is 0.05. Of your sample 0.04. Integrated fluorescence intensities is 0.9. And then what is left? Refractive index of these two is of your sample is 1.4 and of reference 1.33 whole scale. If you calculate it out, the quantum yield of your sample would be 0.47. This is just formula based. It is as easy as it could be. Fine. So answer would be 0.7 B. Is it okay? Okay. So can I move to next question? Okay. Moving on to the next question. Okay. Here it is written maximum emission shift from this 460 nanometer to 520 nanometer on increased solvent polarity. What is the solvent relaxation energy? Means delta E they are asking. This is also very simple. Just convert this 146 10 to the power 7 minus 10 to the power 6 divided by 520. You will get the this in centimeter inverse. Oh, okay, written. It is written here. So it would be 2173 and 19231, and it would give you 2508 centimeter inverse. Approximately 205 2500. Option C is correct. This is okay, I believe so. Any confusion? Okay. Moving on to the next question. Time dependent fluorescence exhaust shift TDFSS experiments are mainly used to probe. So I am doing PhD under Professor Sen, who is taking this course, who is the instructor of this course. And why I'm telling this? Because I'm working on proteins, and this is the instrument, and this is the experiment. This is the experiment, TDFSS experiment. I am using on daily basis, and my PhD is relying on that. So I'm measuring the water dynamics of a protein in the presence of the crowders. So this is very much close to my heart. Anyway, so time dependence fluorescence stops experiment are mainly used to probe. What they are used to probe? As I've already explained, I am measuring the water dynamics. So which one is which one is going, which one is the correct answer? Vibration relaxation ground state? No, because why? Because this is time dependent fluorescence extrusive. So which means we are talking about the excited state phenomena. So here it is written vibrational relaxation in the ground state, which doesn't make any sense. Electronic dephasing of the excited state? No. Time scale of solvent reorganization? That is what I am telling. Water dynamics. So and water is solvent in my case. Reorganization around the excited solute. So my protein is, I am exciting my protein. So basically, protein is inherently uh, not fluorescent molecule. That is why we have to attach or tag a molecule or fluorophore dye to the protein. So we call the tagging. And then somebody wants to join now. Devendra Kumar. Hello Devendra. So where are you from? Hello. Devendra, are you able to see me and able to see the screen? Just reply. Hello sir. Yeah, fine. So what are you doing? You can speak. You can mute yourself and talk to me, because this is an interactive session. So it would be better for you also to interact with me and learn something. That would also be better for me to teach you and gain some experience. So tell me, where are you from? Just introduce yourself, then we will. लाइब्रेरी में है सर. Okay, no problem. Fine, fine, fine. Okay, you can listen to me. Okay, no problem. Okay, anyway, you can write in the chat box, so there is no problem. Even though if you are not able to speak in English, that is also fine. There is no problem. Maybe because there are some people they are shy, so that is why I'm telling you. No problem. There is no problem. Anyway, you can write in the chat box. So I hope you have able to solve the question. This is I'm solving the assignment 3, week 3. So I'm so the instructor of this course is Professor Sen, Pratik Sen from IIT Kanpur, and I'm also doing PhD under him at IIT Kanpur, and I'm working on this field only, time dependent fluorescence shift. So this is I'm using on daily basis. So this is very much close to my heart. I have already told to Patlika and Shivam. They were here since uh, from the starting of the class. So tell me, according to you, What would be the correct answer of this question? Time dependent fluorescence Stokes shift experiment are mainly used to probe vibrational relaxation, electronic dephasing of excited state, and C is time scale of solvent reorganization around excited solute, and fourth one is fluorescence quantum yield of solute. So what do you think? Which one is correct? No answer. Shivam, Patlekha, and Devendra. How do you explain this? Like, what is the correct answer of this question? Okay, Patlekha is saying C. C means time scale of solvent reorganization around excited solute. Yes, that is the correct answer. So, what happens is that, let's say this is your this is your ground state, excited state, and I am drawing I am drawing vibrational relaxation state with this. These are the vibrational relaxation states. Not sorry. Uh, what is the electronic vibrational states? The V0 to V1 to 3. So let's say you are exciting your molecule from here till here, right? Then what will happen? It will it will it will relax to the ground state of the first excited state. Okay, and then what will happen? Molecule is here. So this is very fast. It is in picosecond or something. Then this molecule, so let's say I'm explaining, let's say this is a molecule, plus plus minus minus, here also plus plus minus minus. But when you have excited this molecule from here to here, what will happen? Let's say this mu e is greater than mu z, so this will be plus plus minus minus. So the polarity is higher, dipole moment is higher at the excited state. So the solvent near around it, I'm drawing the solvent. Let's say I'm drawing this solvent. This solvent will get the less time to rearrange themselves. So it will come back here. Basically it will take the time to rearrange themselves, because this electronic transition is so fast that these molecule they will remain at their position because the electronic transition, this transition was so fast they didn't get any chance of the reorganization. Why they will reorganize? Because the dipole moment were here less, here the dipole moment is higher. So the solute, it is inducing the or creating the reaction field for the solvent around them to rearrange themselves to minimize the dipole moment effect. Then they will come to the relaxed state. So when they will rearrange this solvent molecule, blue color molecule, then they will come at here at this position. And then they will slowly come. So in time dependent fluorescence stroke shift, TDFS, FSS, we measure, we try to capture this part, fluorescence from this part. When this reorganization of the solvent molecule around the excited fluorophore is happening, we measure that only. So for better visualization, let me give you something which you can have. Which can make you better understand of this TDFSS. Let me give it. Okay. So I am switching, presenting entire screen. See, look at this. This is what is happening. See the excited state. Are you able to see my cursor? Or I should go to the full presentation mode, then you will not able to see anything. Yes, then it is difficult. Okay, anyway, see, I think you are able to see the cursor. Yes. So see, look at here, this is the ground state, this is the ground state. So from here you are exciting the molecule, photo excitation, it is going to the excited state, and the dipole moment is higher. See, mu e, this is greater, and this is the equilibrium ground state with a small dipole moment, low energy, which means that these are the water molecule. See, look at this water molecule around them. But this photo excitation is so high, even upon the excitation, the dipole moment of this molecule have changed. But the the position, or I would say the orientation of the water molecule have not changed here. Look at closely. See the position of this water molecule to this water molecule, of this to this to this to this. All the 1 2 3 4 5 6 7, all the 7 water molecule are exactly similar to this. But the dipole moment of this excited state have changed. So this solute molecule whose dipole moment have changed upon photo excitation is going to uh, generate a reaction field, which means it will induce some force or induce dipole that will going to reorient this, they will force this water molecule around them to reorient themselves to stabilize this excited state. So but this excitation will take time, of course it will take time. Now this, see, the position or the orientation of the water molecule have changed here. See, so dipole moment was here like this at here. Now, so the dipole moment of the water of this water is like of this water is here and here. So dipole moment of this water molecule is going like this upward direction. So look at here. See, of this in this fashion. See how this have arranged. So I would anyway this I will explain. So this reorganization from here to here, the solvent relaxation time I have written tau s. From here we try to capture the dynamics. This capture the uh, uh, fluorescence from here, next, then next, and then next. So and then we will get the time resolved emission spectrum, that is called that can be captured using the TCS-PC instrument. See the dipole moment of the water molecule. See the dipole moment of the water molecule is exactly same like this, but the dipole moment of have these have changed from here to here. So it will now dipole moment, they are stabilizing, they are cancelling each other. That is why it is a stable state. So we are capturing dynamics of this state. Anyway, so and to show you, give you like this. This is your, this should be ground state. This is not excited state. From here to here, see, like fluorescence at this position, fluorescence is this position, fluorescence at that position. We are capturing all this. I hope it is visible to you. So this is my PhD work. I have shown you. No problem. Where I was here only. Okay, now I to again reshare my PPT. So my PPT is visible. Question answer PPT. Okay, fine. So the answer of this question is C. So TDFS experiment are mainly used to probe the time scale of the solvent reorganization around the excited state solute. Okay, moving on to the next question. According to the Lippard-Mataga equation, the Stokes shift increases more strongly with increase in the refractive index, increase in solvent viscosity, increase in the solvent orientational polarizability, increase in the solute concentration. So according to the Lippard-Mataga relation, shows a linear dependence of Stokes shift on this. I hope you remember the Lippard-Mataga equation, which represent the orientational polarizability of the solvent. If you not remember, let me share the lecture note. This is Lippard-Mataga equation. Are you able to see? Yes, no? Hello guys. Yes. Okay. Fine. So according to this Lippert-Martha equation, what do you think? Where is our PPT? Ah, yes. So according to Lippert-Martha equation, the Stokes shift increases most strongly with. So what is Stokes shift in Lippert-Martha? This is Stokes shift. Mm, this is Stokes shift. This is Stokes shift. So it depends on what factors. See, H is constant, you know. C is constant, you know. And A is, I should write. How I will write here? A. No. This. A. Yes. So A is your radius cavity. Okay. And mu E, mu Z, these both are mu E, mu Z are dipole moment of excited state of ground state, and epsilon and n is refractive index. What is epsilon? Tell me. Refractive index. What is epsilon? Any one of you? Yes, it is dielectric constant. So dielectric constant. Now coming back to our PPT. So orientational polarizability, right? So dielectric means you depend on the solvent polarity, dielectric constant. So why orientational polarizability? Just like the water, no? Let's say this is positive charge. Let's say water like this. So it will go back to this water like this, because this is delta negative, delta positive, delta positive, positive. This is delta negative, this is delta positive, this is, so this not negative, this negative, this negative will try to come back here, and so that is why this reorientation of the water molecule will happen like this. So that is why this Lippert-Mataka equation Stokes shift. So basically, whatever I have shown you in TDFSS, what is happening? Solvent relaxation is happening, no? So that is why the Stokes shift is higher at this condition. See, if the molecule is relaxing from here only, the Stokes shift will be less. But when it is rearranging and then coming back here and then emitting from here, the Stokes shift will be higher. Stokes shift means the difference between the absorption wavelength and emission wavelength. Stochastic is this. This is absorption. This is emission. So stochastic is this. Maxima. Maxima. This is intensity. I hope you are getting this. So increase in the solvent polarity. So Lippard Mataga equation, according to this equation, Stokes shift increases most strongly with the increase in the solvent orientational polarizability. Option C. Is it fine? Okay, Patlika is saying okay. Devendra, is it okay to you? Yes, okay. Moving on to the next question. Okay, this was 8th, 9th question. If the, the slope of this versus orientational polarizability is positive, okay, this I need to show you here. Okay, this equation only, right? Mm-hmm. Okay, this positive is I should take another. Hmm. Slope between plus plus versus orientational polarizability. So slope between absorption plus emission orientational polarizability. This is orientational polarizability. This one, right? Wait for a second. ये ऑनलाइन रिकॉर्ड हो रहा है अभी रिकॉर्ड हो गया है Hello. Yes, I'm back. So 2 epsilon plus 1 n square minus 1 2 n square plus 1. So the slope is, so this is orientational polarizability, this portion. This is already given. So what is the slope? This is the slope. Minus 2 mu e square minus mu, this is e, mu z square divided by something h c a cube. So slope will be, because this is minus, so it is like this. And it is written, what is the question? This plus or minus? If the slope of this versus orientational polarizability is positive, but okay. Okay, the slope is here is negative. In this case, according to the equation, it is negative, but it is given positive, which means then mu z should be greater, no? Mu z is greater than mu e, but answer is different. Answer is B. Mu e is greater. Slope is directly proportional to this. Positive slope means the excited state dipole moment is larger. Are we missing something? Patlekha, Shivam, Devendra, what we are missing? We are missing something. You can write in the chat box also if you don't want to. Uh, okay, so you can write in the chat box also if you. My slope. Because this is already negative. So if this is negative and in question it is positive, which means we have to make this whole quantity positive. To make this whole quantity positive, mu g should be greater than the mu e. Then the whole quantity will become positive. Then the slope will be positive, according to me. So answer should be 1A. But answer here written is B. I don't know why. Slope is directly proportional to this. This is true, but minus is also there, no? This is plus. This is plus. Positive slope, the excited dipole moment is larger. But here, according to me, ground state dipole moment is larger. According to this orientation of polarizability. Maybe something wrong is there, or maybe we are understanding something wrong. Yes, you are right. Answer should be A. Yeah, yes, it should be A, according to me. So maybe this answer is wrong, because as we have seen in the lecture note, it should be like, because slope is not just directly proportional to this. Slope is negative, and something here is c square something, some fraction. 2 is also up at the numerator. 2, something like this. So according to me, B, sir, right answer. Okay, Devendra is saying B, sir, right answer. Okay, how come? Devendra, tell me. Maybe I'm missing something. I'm not able to process right now. Tell me. Are you writing? Because according to me, and Patlika is also saying answer should be A, but you are saying answer should be B. B is also written. So now explain it to me. Because if mu assignment accepted option B, okay, okay, that is different thing. Because answer in the online portal is can be whatever the TA maybe TA or the instructor have made mistake or anything, but they have given option B to the software. They have updated, given the correct option B. So if you have given the option B correct option, then they will accept this. So according to me, answer should be A. Because assignment is maybe instructor is handling or one of his TA is handling. So if they have given the uh, wrong answer, updated their wrong answer, then of course they will accept that only, B only. So according to me, it should be A. Anyway, in the next class we will think, or I will again solve it and tell you in the next class. Okay. Moving on to the next question. Devendra Kumar. Yeah, okay, okay, fine. What about Patlekha? Is it fine? We will move to the like. Okay, fine. Okay, for question number 10. For a solvent, refractive index is 1.5. The electronic polarizability is close to. Oh, this is the direct formula. The electronic polarizability is formula is already written. We just put it 1.5 in the place of the n. You will find it 0.23. This is simple. For a solvent with a refractive index, this the electronic polarizability is close to 0.35. Option B. This is just this formula you already know. I hope so, right? Patlika knows, yes. What about Devendra? What about Shivam? Shivam also knows. Devendra also knows. Okay, fine. Then it is simple. Moving on. Okay, moving on to the next question. So this question is from previous year. Now we are starting the previous year assignment week 3 questions. So Devendra and Patlika and Shivam, you might have not seen this assignment. I have taken from NPTEL last year. So now it's time for you to solve. I will solve obviously, but you need to also um, think about it. Anyway, so first question is in solvation dynamics measurement, the time dependent fluorescence shift is primarily used to. Oh, this is the same question. I've explained like around 10 to 12 minutes. So this is option B. Study the time scale of solvent reorganization. Study the time scale of solvent reorganization. Time dependence fluorescence shift tracks the gradual shift in the fluorescence emission over time after solute molecule is excited to a higher electronic excited state, which means they are saying this. And this occurs because of the solvent molecule reorganize around themselves around the excited state dipole moment of a solute. TDFS is therefore primarily used to study the this study the time scale of solvent reorganization and provide insight into the solution dynamics, particularly how fast or slow the solvent from here to here, from this point to this point, solvent can adapt to a new electronic environment of the solute. So if it is going slow, the dynamics is slow. If from here to here it is going fast, the dynamics will be fast. Okay, now it's your turn to tell me. Let's say I'm measuring the dynamics of one uh, fluorophore molecule C153. So this is the coumarin molecule. This is the fluorophore. Let's say I am measuring this in water. Solvent is, I am giving the solvents. This is molecule, your fluorophore probe. Solvent, A water, A V glycerol, and uh, third one is, let's say, ficol 70. 70 means 70,000. Molecular weight of this is 70,000. Glycerol you know, water you know. Now tell me, out of 1, 2, 3, in which the dynamics will be faster and in which solvent the dynamics will be slower. This is for you. Now you need to tell me. So can I give you a hint if you are not able to think? Fast for water, slow for ficol. How? Why? Viscosity more for what? For ficol, yes. So that is why the viscosity is higher for ficol, because the molecular weight of the ficol is 70. I've already told you 70,000. 70,000 you can imagine, no? Water, what is the molecular weight of the water? One molecule. What is the molecular weight of the water? One molecule of water. 18. And what is the molecular weight of the ficol? Is 70,000. So now you can understand that it is a big molecule. So the viscosity will be higher when the ficol is present. When the viscosity is higher, it is simple for you to like figure it out. That the molecule is going from this position. I should take another. From this position to this position will be slower in the case of the ficol comparison to the water. And glycerol will be in the glycerol, in the presence of the glycerol, dynamics will be slower compared to buffer, but it will be faster compared to the ficol 70. Right? Devendra, is it okay to you? Okay, fine. So, can we move forward now? Okay, Patlika is saying okay. Okay, Moving on to the next question. Next question is, in the context of the Lippard-Mataga relation, the factor contribute to increase in the Stokes shift of a positive solvatochromic solute. Anyone? Okay, let me show you the Lippard-Mataga equation also. So then Lippard-Mataga. Okay, it is written here only. This equation. This is Lippard-Mataga. Okay. So according to this equation, see, the difference between these two is directly proportional to the difference of dipole moment of these two, and this is just depends on the solvent, this full portion depend on the solvent. So when this will increase, which means that the this mu is greater than mu z. So which means the question is saying about the positive solvatochromic solute, means the red shift. So the factor contribute to an increase in the Stokes shift. So difference between absorption minus emission. Difference between these two. And given also the positive solvatochromic solute to increase in the Stokes shift. So the red shift will occur in the case of more polar solvent. If more polar solvent, if mu E is greater than mu Z. So that is what it is written. An increase in the solute solvent interaction and solvent dipole moment. And Lippard-Mataga relation shows that the Stokes shift increases when the solute interact more strongly with the solvent, especially in the polar solvent. The increased dipole moment of the solvent enhances this interaction, leading to a larger shift in the emission spectrum. I hope it is fine, probably. Yeah, Patlika is saying. What about Devendra? Okay, fine. Moving on to the next question. So in reality, the component of the fluorometer are not ideal, which we have already discussed. Because of this, we need to correct the recorded spectrum with the corrected file, which is a unique file for a given fluorometer, including the rectification of a excitation light intensity variation and correction regarding the monochromator and detector. Means your lamp and mono and your detector. We measure excitation spectra by S1 by R1C, considering a hypothetical situation while light source is ideal. Light source is ideal, which means we don't need this R1. But monochromator detector is not ideal, which means we require this correction file. So in this case, the combination that will give the correct excitation spectra is. So according to me, if your light source is fine, is ideal, which means we don't have to normalize it by another detector, which is R1. So this is sample, that is why S. This is for reference, because the light intensity is not ideal all the time. So let's say at this wavelength, light intensity, the lamp profile is like this, something like this. So we have to normalize it. This is the intensity of the lamp. So that is why we have to normalize. Let's say we are observing a spectrum at this position or at this position. The intensity of the lamp is itself is different. So we will always measure the wrong spectrum. So that is why we need to normalize by R1. But it is given here the light source is ideal. So we don't need R1. So according to me, in this case, the combination that will correct the excitation spectra is S1 by C. And this C is because of the comes because of this non-ideality of the mono and monochromator and detector. So they are not ideal. But here in this question, this option is nowhere I am seeing, and the option is given D. I don't know why. An excitation spectra is measured at one wavelength, so it is not necessary to correct S1. That is fine for excitation. And second option is, but we need to divide the output by R1 to rectify the fluctuation in the output signal due to the fluctuation of the intensity of the light source. That, but in the question it is given that it is not needed because the light source is ideal. Now in this case, the light source is said to be an ideal one, which means its intensity remains same always. Hence, it is not needed to divide the fluorescence signal by R1. So only S1 is good enough in this case. According to me, it should be S1 by C. What about you, Devendra? It should, according to me, it should be S1 by C or it should be S1, because the correction file is for mono. Because again, we are measuring, we have fixed the wavelength, we have fixed the wavelength of the emission in the to measure the excitation spectra, but still, but we have not measured it, but we have not uh, considered the ideal monochromator and detectors. So in the same, where the sample is placed, where we are observing the fluorescence or this excitation spectra, their wavelength is also changing. maybe it is not dependent on the, because mm, maybe because now where we are observing the signal. Let's say this is your detector, here is your monochromator, this is mono, this is detector, here is your sample, here is your detector dr, this is ds, this is reference, this is, and here is the light source. Now we have fixed the wavelength, observing only one wavelength. Maybe this option is also correct as one, because at here the sample is here and we have fixed the emission maxima, now observing the lambda excitation, and this lambda excitation, mm, but we are measuring here only, right? Because of the sample s is there, no, we are measuring here, even though we have excited, but it should be like mm, at only one wavelength, but this, all the wavelengths are not equally coming, the photons are not, intensity is not same. Also monochromator detector efficiency for excitation, maybe this could be s1, I don't know, I'm not able to think right now. According to their answer, according to me it should be s1 yc. Maybe there is some catch here, I'm not able to get it now, but uh, okay. So now today we are closing the session because it's already 6:03. Come back in the next class, we will solve other questions also. Till then, bye. I'm closing the session. Join the next session. Devendra Patlika Sevam. It's already 2 hour. Okay, bye.